Remember that these videos are just a preview, so we won't have time to cover everything about the retentive instructions, latches and unlatches, but even so, there's still a lot to cover here, so we'll have to pick up the pace. Just play the video again if you miss anything. Notice that our inputs are momentary push buttons and that button B is wired normally closed in the field. One of our objectives is to compare the operation of the seal-in rung, highlighted in yellow, with the operation of the latch and unlatch rungs, shown in blue. Many people assume that the operation is identical and that the two methods can be used interchangeably. That's not correct, and serious safety issues can result from this misconception. Both of the output devices in the field are off right now. The system is waiting for the operators to start it up. Now the operators press the start buttons, and it's time for step 1 of the scan cycle. Do we have current here? Yes. So the bit contains a 1. Do we have current here? Yes. So the bit contains a 1. Do we have current here? Yes. So the bit contains a 1. Do we have current here? No. So this bit contains a 0. Most stop buttons are wired normally closed for fail-safe operation, but there's a perfectly valid reason why stop button D has been wired normally open instead. We won't have time to talk about it in this short video, but we'll cover the details when you go through the boot camp. And for now, remember that we're using a PLC 5 system in this lesson. And now for step 2 of the scan cycle. This says go look for a 1. Do we have a 1? Yes. So this is true. This says go look for a 1. Do we have a 1? No. So this is false. This says go look for a 1. Do we have a 1? Yes. So this is true. We have a continuous path, so this has true coming in. So the processor goes to the bit and writes a 1 into the box. This says go look for a 1. Do we have a 1? Yes. So this is true. And this has true coming in. And the rule says if true comes in, go write a 1. Let's make a quick comparison between the rules for the OTL latch instruction and those for an OTE. Notice that they both go write a 1 when true comes in, but the latch does nothing when the processor executes it with false logic. Now back to the scan. So based on the true logic coming into the latch, the processor goes to the bit and writes a 1 into the box. Many people believe that a 1 written by a latch is somehow different from a 1 written by an OTE. That's not correct. The most common misconception is that once a bit has been turned on by a latch, then it can only be turned off by an unlatch. That's wrong too. Actually, anything capable of writing a 0 into the box can easily turn off a latched bit. Now let's move on. This says go look for a 1. Do we have a 1? No. So this is false. And this has false coming in. And the rule says if false comes in, do nothing. Another quick comparison. This time none of the rules match up. There's a lot going on here, but remember that this video is just a preview. You'll cover the details by working through plenty of hands-on examples when you get to the class. But now here's the end rung. And now step 3. There's a 1 in this bit, so the module gets a signal to turn the output on. And there's a 1 in this bit, so the module gets a signal to turn the other output on. And now both output devices in the field are on, and we're through with this scan cycle. Next, let's see what happens when the operators release those start buttons. And it's time for step 1 again. Do we have current here? No. So the bit contains a 0. Do we have current here? Yes. So the bit contains a 1. Do we have current here? No. So the bit contains a 0. Do we have current here? No. So this bit contains a 0. Now for step 2. This says go look for a 1. Do we have a 1? No. So this is false. This says go look for a 1. Do we have a 1? Yes. So this is true. This says go look for a 1. Do we have a 1? Yes. So this is true. We still have a continuous path, so this has true coming in. So the processor goes and writes a 1 into the bit. This says go look for a 1. Do we have a 1? No. So this is false. This has false coming in. And the rule says do nothing. This says go look for a 1. Do we have a 1? No. So this is false. This has false coming in. And the rule says do nothing. Which brings us to the end of the ladder file. Now for step 3. There's a 1 in this bit, so the module gets a signal to turn the output on. And there's a 1 in this bit, so the module gets a signal to turn the other output on. We're through with another scan cycle, and here's a screenshot of our present conditions. One output is being held on by a seal-in rung, the other has been latched on. So far, these two programming approaches appear to be identical, but a big difference can show up whenever the PLC system enters the run mode. Let's work an example, starting with our present up and running conditions. Now suppose that the main power to the plant has just failed. No power means that the output devices in the field go off. But notice that both output bits still contain a 1. So the big question, what's going to happen to the output devices when the power finally gets restored? To answer that question, we'll need to know something about pre-scan, which is part of the warm-up routine that an Allen Bradley processor goes through every time it enters the run mode. We won't have time to talk about how pre-scan affects everything, like timers and counters and one-shots, but we'll at least cover the 3 output instructions being used in this lesson. Now suppose that the system power has just come back on again. As part of its warm-up routine, the processor automatically runs through one pre-scan sequence. Notice that any input condition on the rungs are completely ignored. Pre-scan has its own set of rules. The processor comes to the OTE for lamp E. The pre-scan rule for an OTE tells the processor to go write a 0. So the processor goes to the bit and writes a 0 into the box. Next, the processor comes to the latch for lamp F. The pre-scan rule for a latch tells the processor to do nothing. So next, the processor comes to the unlatch for lamp F. The pre-scan rule for an unlatch tells the processor to do nothing. Then the processor comes to the end rung, and we're through with this example of a pre-scan sequence. And notice that pre-scan caused the OTE instruction to change the bit status of lamp E to a 0. On the other hand, pre-scan let the latch and unlatch instructions leave the status of lamp F unchanged. That bit still contains a 1. With Allen-Bradley systems, the difference between retentive and non-retentive depends on how pre-scan affects the different types of instructions in the program, not on special ones being stored in the bit boxes. Now that the pre-scan is done, the status of these 2 bits will be what the processor sees when it finishes warming up and starts making its regular scan cycles. Let's cut right to the chase and see what's going to happen the first time this seal-in XIC sends the processor to go look for a 1. Because of the pre-scan's effect on the OTE, this bit does not contain a 1 anymore. So this will be false, and we'll lose our seal-in logic path. And the first time the processor does step 3, lamp E will stay off until somebody pushes the start button to seal it in again. But lamp F will retain its latched on status and automatically come back on again as soon as the power gets restored. Here's a screenshot of our present conditions, and now here's the main point of the lesson. Suppose that instead of just harmless lamps, our outputs in the field happen to be machines instead. Improperly using a latch arrangement could cause a dangerous piece of machinery to unexpectedly restart after a power failure. On the other hand, incorrectly using a seal-in arrangement will not restart a critical piece of machinery that we really do want to come back on again. The misconceptions about seal-in and latch and unlatch programming approaches can cause some big surprises whenever the PLC system goes through a startup sequence. You need to be aware of the differences. Let's finish up with a quick review. We started out in Lesson 1 with a problem that many PLC technicians cannot answer, even some technicians with years of experience. This pointed out that the way many people look at PLCs is wrong. Wrong because it's based on mistakes and misconceptions that don't always work beyond the beginner level. In Lessons 2 through 8, we gave you a preview of how you'll learn to look at PLCs in our boot camp classes. We gave you a set of simple rules that can be systematically applied to any problem, regardless of how tricky or complicated it might appear. These rules work because they're based on exactly how the PLC operates and not on watered-down beginner-level explanations. Then in Lesson 9, we gave you the solution to the original problem from Lesson 1. Following our step-by-step approach made it simple to analyze the PLC's operation and to understand exactly why it acted the way that it did. Once in a while, someone tells us that we just have another way of looking at PLCs and that their old ways work perfectly fine. We never need to argue because exercises like Lesson 10 always convince hardcore skeptics that our boot camp approach always works and that quite often their old switches and coils and green means true methods do not. Usually these disbelievers become our most enthusiastic students once they realize that we're offering the answer to years of confusion and frustration. Lesson 11 introduced the basic ideas of pre-scan and why latches and unlatches behave the way they do every time the PLC processor enters the run mode. At least 99% of the students who come to our PLC boot camp have already been to other training classes, usually with very poor results. These video lessons have shown you one of the reasons. In many cases, the material that they've been taught is actually wrong. You'll find other reasons by reading through the boot camp experience on our website. Let's just say that we don't do the same old PLC training as usual that you've been through before. We hope these lessons have been helpful in giving you a preview of what to expect when you come to one of our classes, and we look forward to meeting you in person soon.